So let us begin. It is a great pleasure to welcome Chiara Marletto from Wolfson College in Oxford, I believe. And she's going to tell us about beyond quantum computing, the physics of can and can't. And I think that looks very close to the title of your recent book, the last part of it. Okay, yes. So thanks for joining us.
Thank you very much for inviting me to give this talk. I'll just kind of share. Okay, now you should see the full screen version of this. And yeah, so the title is a bit provocative, I guess, and it's a more poetic version of the physics of can and can't. Is more like a sort of poetic version of this thing that's called constructor theory, and that will be one of the methodology that we're talking about in the seminar. And so I thought I'd pick two applications of this approach. So the first one will probably take us a bit longer because I'm going to introduce some sort of background. And then after this first application, we'll move to a second one, which is more like in the direction of thermodynamics. And then I'll wrap up. So, and as I said, I'm very happy to be interrupted, and the talk is designed to be informative, but if there are things that are not clear enough and compromise the rest of the talk, I'm very happy to clarify them a bit more as we go along. So just interrupt me if you want. Okay, so first thing, wanted to clarify why is it that we want to go beyond quantum computing? So why even having this sort of idea? And I like to introduce this problem situation by noting that quantum computing, on one hand, it can be regarded as a kind of revolution because it somehow taught us that there is something to be said about computers, which are in a way macroscopic objects that not really usually traditionally regarded as part of fundamental physics, which can be actually important to understand the foundations of some of our deepest theories of nature's quantum theory. And so that was a slightly odd idea that initially was resisted by, let's say, part of the community, and then it was accepted, and then it even led to some technological developments, which is this quantum computation technology that's now quite widespread and researched around the world. But from the theoretical point of view, which is my interest, the revolution is somewhat unfinished, because if you look at how quantum computation is formulated, most of its theorems are based on the quantum formalism. So they usually refer to things like unitaries and Hilbert spaces and so on. And somehow this is at odds with the generality of, say, classical computation theory or information theory, which is very general and doesn't have necessary roots into specific dynamical formalism. And if you consider the fact that quantum theory may have to change because, for example, we want to have a better theory that fully incorporates gravity, or maybe because we want to solve some problems at the foundations of quantum field theory and so on. This is a bit it's kind of problematic, because we would still like to have theorems about the universality of computation and so on, and about channel capacity, etc., without having to rely necessarily on the formalism of quantum theory itself, so that they would hold even if quantum theory were to be modified. And so the first question that kind of takes us a bit beyond quantum computation as we know it today is the question of whether, can we have a quantum theory of information or computation without quantum theory itself, so without the formalism of quantum theory. So that's kind of the first reason why we might want to generalize quantum computing. The second reason is that quantum computation is a sort of study of let's say the properties of this universal quantum computer, And, in that sense, you could think that's very exhaustive because we're putting quantum theory together with the idea of a universal computer, which, as was defined by Turing, is a programmable computer whose repertoire includes all computations that are physically allowed in a given physics. And so in that sense, it sounds very general. But there are things that are not included in this general scheme of computation. And these things are tasks, general tasks, which are not computations. So they are kind of more general than simple computations. And one example is self-replication or self-reproduction. So this task of creating a copy or a replica of oneself is a task which is physically realizable, obviously, because physical systems do it all the time in biology. But the universal Turing machine doesn't have in its repertoire this capability, so it can simulate this, can be programmed to simulate in its kind of workspace self-reproduction of another object. But if you wanted to program it to create a copy of itself, a Turing machine can't do that. And this is an observation that was already clear to von Neumann. I think von Neumann, among the many things that he was interested in and that he studied, he was really interested in trying to emulate with a kind of programmable system all the properties of living beings, and the self-reproduction capability or the self-replication ability was, of course, one of these key features. And as he was studying this, he realized that Turing machines can't do that. And that's why...
May I jump in with a question? So very, very naive questions. I'm going to warn you from the beginning.
Yes.
I always, like, when I think of a quantum computer, for me, the immediate alternative to which I compare it would be a classical computer or a normal computer, which still does not do self-replication.
No.
So why is the self-replication such an important issue in quantum computing?
Well, it's not important in quantum computing, it's part of physics. So in a sense, if you want, I was saying, if you want to generalize quantum computing, there's another direction in which you can go, which is to make it relevant for more general machines, right? So it's a bit like thinking, okay, I have a nice theory that now can describe some properties of computing machines, both quantum and classical.
Yeah.
And how can I generalize it? And I think I'm now introducing a second direction, let's say, in which I can go in order to generalize that, which in fact was introduced by von Neumann.
I see.
And he wanted to say, we call this Turing machine universal, both the classical version and the quantum version, but they're not universal in the physical sense because there are physically permitted tasks, for example, self-reproduction, which cannot be emulated or implemented by the Turing machine. And that's interesting. So because he then thought, okay, maybe there is a more general machine, and that's why he introduced this universal constructor. So in that sense, it's important, if you like, because, there's a cute argument that von Neumann has about the fact that if a universal constructor is possible, by definition of a universal constructor, it has to be able to create a copy of itself. So there is a self-referential aspect to the task of self-replication, which is specifically interesting, not just because it's happening in biology, but it's also interesting from the, let's say, I guess, computation point of view and mathematical point of view.
So if I may go back and ask even a more naive question, I don't know why, but I always thought what kind of inspired the whole quantum computation direction was the need for quicker calculations, the need for speed, let's say. But so I mean, that's a different direction.
Oh yeah, I mean, I think it's a misconception. So, I wouldn't say it's a misconception. Let's say it's maybe one aspect that's been emphasized a lot about quantum computing is the application aspect, which is perfectly right, and I think it's the one that everyone uses to perhaps sell the idea in a way.
Yeah.
But if you look at, say, what the pioneers of quantum computers did, for example, Deutsch or Feynman, etc., Benioff, they really wanted to understand whether what are the physical limitations of a computing machine, in the sense, the same way that, say, in thermodynamics, you want to understand the limitations, the physical limitations of a heat engine.
Mhm.
And in that sense, it's not really to do with speed necessarily. I mean, it so happens that the universal quantum computer can perform algorithms that are faster at some tasks.
Yeah, I
But
see. Okay.
but the fact of, there's this idea of computational universality. The fact that the laws of physics allow for a machine that's a universal computer, it's a very interesting property of the laws that we know.
Mhm.
It so happens it's true both for a discretized version of classical physics
Mhm.
as well as of quantum theory.
Mhm.
But it need not be true of all possible dynamical laws that you can come up with. So it's
I
a
see, yeah.
property. And I think that was one of the motivations why, physics got into the business of quantum computing in the first place.
I see. Okay, yeah. So the inspiration came from the fact that we're looking at the limitations of this classical computer.
Yes.
Yeah.
Yes. And what happens if we run the scheme of Turing on different dynamical laws? And that's what, that's the quantum computer. And now von Neumann is asking a different question. He's asking, okay, what about general programmable machines that can perform more general tasks than just computations? Can we have a theory of those?
Yeah, perfect.
Yeah.
Thank you.
No, great questions. I think it's very nice because, I mean, the concept of universal constructor is very interesting. It's just sadly somehow, well, I guess it hasn't been developed really nicely yet. And I think that's why I'm kind of putting it into the motivational part of the talk.
Thank you.
Yeah, so von Neumann thought, how can we go beyond the scheme of the universal Turing machine? And he conjectured that there could be a more general machine that's called the universal constructor, which is defined as a machine that can be programmed to perform any task, not just computations, that is physically allowed under a given set of laws. And then, of course, I mean, you can think of this as being popularized as like a universal 3D printer. And among other things, if it's allowed as an object, because it's got to be able to build anything that's physically possible, should be also able to build a copy of itself.
Sorry, could I just ask a potentially silly question again? You said before that the universal computer couldn't replicate itself, and I was trying to see how that statement comes about. I was imagining this kind of a thing where you have a 3D printer or some machine like a car factory or a computer factory that just builds another computer or itself. What's wrong with that picture, and how does that not fit into the?
Well, so the Turing machine is very limited as far as what it can do. So it's got a tape, and it's got things that it can write on the tape, and then an eraser as well. So it doesn't have arms to build anything. It doesn't have physical parts that are allowed to.
Oh, right. Okay.
So there's no assembly part. And it might look trivial, but it's actually not trivial at all, because the fact that Turing machine is defined in such a way that it can only erase and write on an infinitely long tape is a definite characteristic thing that Turing used to define his machine. And if you want to incorporate something more general, you really need to redefine the structure of the machine completely. And that's, I think, I mean, if you're interested, I think von Neumann has very interesting writings about, what is the minimal architecture for a universal constructor, how many parts it has to have, and how many more parts it needs to have more than, say, the Turing machine, and so on. But typically, so what in other words, you can always get a Turing machine to simulate on its tape, like in the workspace. You can have virtual reality with replicators, like, I don't know, like Conway's Game of Life, if you like, his gliders and stuff. But those are not self-reproducing. So it's not a self-reproduction of the Turing machine itself. And that's not by chance. It's not just because we haven't built one. It's just we can't do it just because the scheme that Turing came up with doesn't allow for that kind of task. And it's interesting. I think von Neumann's observation was really interesting.
Okay.
And
that makes sense. Yeah.
Yeah. So I think the idea is, can we have a generalization of the quantum theory of computation to include universal, possibly quantum constructors, and what would that look like?
Because you could imagine a classical one.
Yes, of course. Yes, you can also imagine a classical one. And there's an interesting argument, I think, as to why there cannot be a classical universal constructor if there is a quantum, if you're under some quantum laws. So that's an interesting aspect. I mean, I can talk about it maybe later, but I think there's a nice If you read, I think David Deutsch's paper on this general theory, you will find a cute argument that's interesting. So constructors are different from computers because they can build things. So for example, if you have two constructors, you can have one of them. So if you have a constructor with another constructor in its repertoire, the first constructor is automatically also includes the repertoire of the second constructor, just because it can build the second one, which can build then whatever you need. Whereas with computers, it's not like that. There's no such thing. If you have two computers that, one does addition, the other one does multiplication, you can combine them in some ways, but not in this way. So you can't have a computer that builds another computer that can do multiplication. There isn't such a property of composition of computers. So I think constructors and computers have very different properties, and that's why they're interesting, I guess. Okay, so these are the two motivations, I guess. And now I'd like to argue that one way to go about this business, both to try to construct the theory of the universal constructor, as well as of trying to generalize the quantum theory of computation by kind of making it somehow dynamics independent, emancipated from quantum theory, is to dig a bit deeper into the foundations of physics, and note that there are some aspects of physics, of theoretical physics, which are already phrased in a way that's conveniently independent of specific dynamical theories, and it's also conveniently phrased in order to constrain the repertoire of a machine like a constructor. And I call these counterfactual physical principles, but they're just very mundane things that we use all the time. Of course, I mean, we have like the conservation of energy in the form that says that perpetual motion machine is impossible. Then, you can think of the second law, which says it's impossible to build a machine of a certain kind, which, for example, in this form, it says you can't convert all heat into useful work with no other side effects with a cycle. And then there is the foundational, the most fundamental principle, I would say, of quantum theories, which is the Heisenberg uncertainty principle, that says it's impossible to, if you like, copy reliably all states of a quantum system, which is kind of another version of saying that you can't measure two different observables that are kind of mutually independent to arbitrarily high accuracy. And so all of these things are about impossibilities in a sense, and they're interesting because they can be phrased even formally without referring specifically to a particular dynamics. So that's interesting because it kind of makes you think that you can generalize this idea and generalize this Ken and Kant approach. That's where the kind of name of the talk comes from.
Sorry. Yeah. So you're saying these sort of principles can be phrased in some way without reference to some dynamics, yes, some differential equation or something.
Yes.
How, maybe you're just about to go on to say all this in more detail, but how does that work exactly? For me, I feel like I could change the whatever differential equations such that.
So you can prove, for example, that Lagrangian mechanics satisfies, I don't know, the conservation of energy. But if you take, say, the foundations of, the conservation of energy is formulated in thermodynamics, you can define it with, once you have an energy function of sorts within a given theory, you can just say that function can't be changed without side effects. And this statement only requires to specify the impossibility of a task. You don't have to commit to a specific, formalism like Lagrangian formalism or a different formalism. You don't need a dynamical equation to state the law. And the second law is the same. The second law actually, in fact, in thermodynamics is formulated without dynamics. The dynamics comes in with statistical mechanics, where you're trying to show that somehow the second law emerges from dynamics. But the good old Kelvin, Clausius, Planck's formulation of the second law, defines heat and work in some way. You've got some definitions for those two things, and then you can state it like that. And it doesn't have dynamics in it. In fact, it constrains dynamics.
I'm not sure if I'm just thinking of this in the incorrect way, but it feels like sticking to systems where, say, energy is conserved is just like sticking to a class of differential equations. And then there are some differential equations that if we said that they were the laws of the universe, then energy wouldn't be conserved. So is that just another way to think about it, or is it?
Yeah, if you like, you can think of it as, differential equations could be formulated. You could have finite difference equations. So you don't have to have even like first of all, for example, you don't have to have a specific space of states. So long as you have a set of states with some even topology defined on it, you may not need more than that. You can still talk about a task being impossible. So you don't really need differential equations for that. You might need it if you want to define more things.
Yeah.
For example, the rate of change of something or something.
Yeah.
But here the game is to say, supposing I want to drop the assumptions about Hamiltonian mechanics in classical physics, or about, say, the Heisenberg equation of motions for quantum theory, or the equations of quantum field theory, and so on. I can drop all of those things, and I can still talk about conservation of energy as the impossibility of a certain task. That's interesting because, as you say, then, if you like, you can then specify more requirements about your dynamics, and then that will single out this class of dynamical laws. But they will be very different from each other. Some will have Hilbert spaces, some won't. Others will have, a set of a space of states that's very, very, very unlike the ones we know now.
Yeah.
And in a way, I think this was the role of, that's why somehow principles were supposed to be important at some point, or at least that still are. I think physicists still use them because they are useful as guidelines, right? When you're thinking, I want to guess a law for this particular system, the more constraints of this kind you have that are robust against changes of specifics of the dynamics, the better, in a better position you are, because you can then have a kind of a hint as to what the new law might look like.
Mm-hmm.
So I guess Einstein was doing something like this when he was trying to conjecture initially special relativity, because he tried to formulate some very, very, very general constraints. Of course, he was also using other constraints, I would say, but I think that was somehow the logic back then. And many others also tried to do.
Of course, yeah.
So in that sense, I regard these principles not as derivative of dynamics, but I don't think I'm saying new really. It's more like there are two philosophies, if you like, to look at what's fundamental. And some people like to think of the principles as being more general and the dynamical laws as being constrained by them. And then you can think the other way around. Principles are actually derivative of the laws. And I'm kind of advocating, say, the first position.
Yeah. Okay. Yeah. But there is some tie there between what's possible dynamically and these guidelines that you put down.
Yes. But it will become a bit clearer later that possible tasks are not necessarily dynamically allowed transformations only. So there'll be they are they're defined in a more general way. So.
Yeah. Okay. No. That's Sorry. I'll let you get on. Thanks. Right. So this is where I think I anticipated a bit this. So in a way, following this kind of logic, you stumble upon this. You end up with this philosophy that I think so. David Deutsch outlined in his paper, which I kind of call the constructor theories program, if you like. And this program says something like that fundamental laws are expressed as these scale-independent principles about which tasks are possible, which are impossible, and why. And I'm going to explain what possible and impossible means in a moment. And then the dynamics and the boundary conditions or the supplementary conditions or initial conditions are a consequence of these principles. So they are explained in terms of principles and not vice versa. And so I think this was something that tries to generalize this idea that is already there in quantum computing,
that there are some principles you can state without kind of appealing to dynamical laws specifically, which are obeyed by, for example, universal computers. The universality of computation is one of these principles, which can then tell you something deep about the dynamical laws that are compatible with them. And David here was trying to kind of generalize this idea to a much broader set of things. And so that's what kind of got me interested into this program back then when I was a student. And that's how I kind of started dabbling a bit into this. And so now I'm going to tell you just kind of few basics of constructor theory, basically what it means for a task to be impossible or possible. And then after that,
yes. Sorry, I have to ask a question.
Yes.
Is this whole thing independent of a background metric? For example,
so let me,
let me finish the question. For example, de Sitter space, there is no translational invariance. So the statement that energy conservation is universal is not true in the de Sitter space. Okay. So, and there is scale. What is meant by scale? That requires a metric, at least to define volumes. Okay. So
well, scale, you can define scale as just the measure of a system. So you don't need, I mean, you need a topology for that. You may not need
topology will not give you this scale.
Well,
topology
you can
give some coverings. What is it? Local coordinates and
okay. So I think you're going very specific into the. So okay, let me just. So first thing is to say that the stuff I'm going to say now is non-relativistic. So I'm going to, so just like good old quantum computing, the results I'm going to state now are kind of meaningful in some approximation where general relativity is not important. So that's one
non-relativistic means you're using a metric, the Newtonian.
Yeah, I don't need to worry about that because I'm just, let's say it's local in space and time, what I'm going to say. I don't want to worry about these effects just because it's not relevant for what I'm going to say. If you want then to define, so scale independent, you can define it in the same way that say you would within thermodynamics. If you want a precise mathematical definition, you can, if you want to attach a metric to that, that's fine. But it doesn't, it's not, I don't think it's relevant for what I'm going to say. I think I'm talking here in very loose terms. So long as you have a definition of scale in a theory, whatever principle constructor theory has, if this theory is compliant with constructor theory, it will hold at all scales. So that's the idea that I have. So what scale means is for a specific subsidiary theory to define. So constructor theory is a bit agnostic about that.
So it's presumably a counting scale you have in mind rather than...
Sorry, say again?
It's presumably a scale in the sense of counting that you have in mind.
Yes, if you like, you can think of it like that. Yeah, yes. But just to give me an example, the second law, as we know it, is not scale independent because it holds at a certain level of coarse graining or in a certain limit, which is a thermodynamic limit, etc. Whereas, say, the conservation law is scale independent as it's formulated. And then you can say whether it's false or true, of course, but as it's formulated, it doesn't refer to scale. So long as there is a definition of energy in theory, then you can, the law says that thing should be conserved. And it doesn't matter whether it's an object that is made of lots of subsystems or it's just a single system.
Yeah.
Sorry. Yeah, it's a very naive notion of scale. So I'm not trying to be very specific in terms of mathematics.
So again, one more question. I don't see anywhere the expression of causality, okay, which is very central to quantum field theory. So where does it fit in?
Well, I mean, I haven't quite explained the theory yet, but I think causality is built in the principle of locality, which is something I will assume throughout. And so if you think about the condition of microcausality, this is kind of one expression of the principle of locality that I have to assume in order to prove all of these results. I'll mention it later.
Sorry, Chiara. Are you assuming a finite system? Is there any assumption of finiteness?
Yes, I think I'm assuming ideally we're dealing with, yes, I mean, all the things I'm going to say can be generalized to infinite dimensional systems, but for the purpose of what I'm saying, I prefer to deal with finite systems because you know the theorems are more easy to consider and so on. So for the moment, I mean, if you want to have something in mind, just assume I'm talking about qubits and systems that can be made of a finite number of qubits.
I think Tony has a question as well. Do you want to go ahead, Tony? Maybe not. Okay. All right. Thanks.
Yeah. So don't take what I write here as so this notion of scale independent is if you like, is a loose notion, and I don't want to formalize it precisely. So just don't get worry about the specific definition because it's not important in this context. Okay. So
when you talk about, can you come around?
Sorry. Sorry, I didn't hear you. I think there was a question, but I'm not sure.
I don't think the question was towards you. I think somebody.
Oh, okay. Then I'll continue. So so just to close this introductory part, the theory has really two roles. So on the one hand, you have to think of it as an expansion on the quantum theory of computation to include the universal constructor. And in the other, the other direction is to think of using, of defining a new set of physical principles that will be used in order to emancipate quantum computation from quantum theory itself. And these principles should be, general enough to unify properties of quantum and classical information. And so in the sense, they should also help us understand what can go beyond the dynamical laws that we currently know. So these are the two roles of the theory. And I will kind of mention both in the applications I will tell you about. Okay, so now let me just have a small digression and tell you some very basics, kind of basic ideas of this constructor theory, and specifically what it means for tasks to be possible. Okay, so as I said, let's say you have a set of theory that we can call subsidiary theory, which has a structure that includes an allowed set of states and a partition into subsystems. Again, this implies the number of mathematical tools that you need for that, and I'm assuming that the theory has them. Then you can define an attribute as a set of states. So it's a generalized physical property, if you like. And then a task is, again, another set, but it's a set of ordered pairs of input-output attributes that specifies a transformation. And this transformation can be either possible or impossible. To explain what possible means, we need to introduce the notion of a constructor. And this is important. So a constructor is a physical system that whenever it's presented with the input states of the input attributes of the substrate, delivers them in the right output attributes as the task specifies. An important thing is that it retains the ability to do this again. So it's not, it's not any part of the environment that can cause a task or a transformation, but it's an environment that in a way can work in a cycle to perform the transformation. And so you can think of it as a catalyst or more generally, thermodynamic cycle or something like that. And the name comes, of course, from von Neumann's idea, just that this constructor now is specific for a task, so it's not universal. Von Neumann's idea was about a constructor that could have in its repertoire all possible tasks. So then for the notion of a constructor is useful to say what it means to be possible, because so the task is impossible if there is some law of physics that says it cannot be performed to arbitrarily high accuracy by a constructor, and it is possible otherwise. And so again, you know, conservation law come to mind as an example, because conservation of a given quantity like energy states exactly that it's impossible to change the energy of a substrate, but you know, other transformations, like for example, copying two orthogonal states in quantum theory are possible, and there's no final limitation on how well you can do them. So it's kind of important that, so in this way you can see that a possible task doesn't necessarily correspond to a dynamically allowed transformation. So it's a more general class of transformations. And the distinguishing feature is that for possible tasks you have a constructor, and for impossible tasks you don't. This is a very shorthand way of saying what the distinction is.
Sorry, could I ask a question about the energy thing again?
Yes.
So what about like, so I'm trying to imagine a situation where I start off with whatever substance and then I want to just increase its energy.
Yes.
The constructor in that case could be like, you know, your oven or something, and you're putting in. Right. Yeah, but
it needs a side effect. It doesn't work in a cycle. So the task of changing the energy of a substrate is impossible, because by itself you can't perform it. Of course, you can perform changing the energy of a substrate and then changing the energy somewhere else.
Yeah.
Right. So the point is that you can't have a cycle that only changes the energy of a substrate if the energy is conserved.
But so in saying that, then you are including in the whole definition also like what the constructor is made out of, or its parts are included in this.
Yeah, so you don't mind the particular architecture of the constructor, so long as there, so if the law says that there cannot be any, that says the task is impossible, so it doesn't matter what it's made of.
Yeah.
And if there is no such limitation, then the assumption is that it's possible. It means that there must be one way, or more, usually multiple.
Okay. So does the input state include the state of the constructor itself? Because you want to have that being like the same afterwards.
No. So the task is specified. So it's like input output. There's like X goes to Y, let's say, and that's only, you know, that's the desired stuff that you want to change. Mm-hmm. And then possible means that there's a way of involving the environment in such a way that it interacts with the substrate, performs the transformation, then stays invariant in the ability of causing the transformation again, and nothing else should change. Because otherwise, so the task includes everything that changes in the process in question. It's not allowed. So if you need part of the environment to change, then it's not going to satisfy the definition of a constructor. And so you would have to include it in the substrates if you like to find a possible task.
Does it kind of translate into like something happening in a closed system?
Say it again, sorry.
So to me, it kind of analogous to saying, you know, in a closed system, you can't just increase the temperature of.
Yes, that's one way of looking at it. The only thing is that sometimes when you allow for a system to interact with the environment, mm-hmm. more things are then possible than what you can do just by thinking that it's a sealed system.
Yeah.
Even though the environment is then going back to its original state in a way like a catalyst, right? Yeah. So that's the thing that's interesting, I guess.
Absolutely. Yeah.
And it's more interesting than just looking at whatever you can do to a system by allowing it to interact around, you know, with any environment, because of course then it's not that's not very restrictive in the sense that environments will cause some transformations, but the thing that we are looking for here is that the environment has this extra feature of being like a catalyst, so it can reproduce, it can repeat the task.
What was your response to like the just going back to the example that the oven couldn't repeat the task again and again? Like,
well, the oven needs electricity to work for one.
Well, and
So
that electricity and extra energy that's being pumped in can't just be part of the constructor in the.
No, because it's used up. If you don't have an unlimited supply of energy, at some point you will run out of it, and then it's not a constructor anymore. So in fact, it's not a constructor, period, because you can't repeat the task. It's a bit like, you have a battery and then you use it a number of times. That's not a constructor because it runs out of energy.
Right.
Whereas,
whereas
if you have a frictionless system and you start it and then it keeps going, that's an example of, if you like, the dynamical laws are there, kind of an example of a constructor. It's a trivial one, but it's a highly idealized example. But what I'm saying is that you don't need side effects for that transformation.
Yeah, but I don't know, there's still something that sounds a bit odd to me, and like in the catalyst example.
Yes.
Don't you have to put in work to bring the catalyst into contact with whatever else you're doing, and you have to do that again and again to use it?
That's part of the construct. I mean, the catalyst is a kind of example that I gave, for something that works in a cycle. Of course, you need the lab. You need the some aspects of the environment to be there as well for the catalyst to work.
Yeah, like the people, they come in and do the.
Well, yes. I mean, so of course you have to think of also of approximate constructors. All of these examples that you're mentioning are approximate constructors. So in a sense, the law that says that the task is possible says that there is no limitation to how well you can you can approximate the behavior of a perfect cycle. So the catalyst itself is not a perfect cycle.
Okay, but so is it just the case that with the definition given, there's not a perfect constructor? But that wasn't a goal that you were trying to get to or something.
No, because there is a difference between saying that the behavior of an ideal constructor can only be approximated in some limit, and the statement that says instead that there is a finite limit to how well you can approximate the behavior of a constructor, and you can't go beyond that. These are two very different statements, mathematically even. And the case of an impossible task is precisely the statement that says that there is a finite limitation to the accuracy to which you can implement the constructor for a given task. So no matter how much you tried, what materials you're using, how many resources, you will always fall short of a given finite amount. I mean, the best example I think is in quantum theory that I can give to you because it's maybe easier to understand. If you have two orthogonal states, a constructor for copying them is possible. There's no limitation to how well you can implement this copy operation under the dynamical laws of quantum theory. But say if you want to copy two non-orthogonal states, then there is a specific final limitation to how well you can approximate a copier. And that's the final limitation is given to you by the inner product of the two states. It's a function of that inner product. And when, of course, the inner product is 0, then you can get arbitrarily high accuracy. But if you try to do it for non-orthogonal states, then you can't. So I think this is the.
So, but in that example, then you are allowing to go from the ground state of the hydrogen atom to the next excited state, which would be orthogonal in that case.
Well, I mean, depends what you're assuming. If you want to, so again, you can think of the degenerate eigenstates of that are orthogonal.
But
if you want to
specifically non-degenerate ones, because then it's back to the issue of. Well,
if they're non-degenerate, then you can't do it. You need side effects, yeah. But the fact that copying is defined in a different way from doesn't talk about energy. I'm talking about copying of two general non-orthogonal states or orthogonal states.
Mm-hmm.
And I'm not thinking of necessarily eigenstates of energy. Because then I would have to consider the limitations of energy conservation. You can have a quantum computer that just deals with, say, like orthogonal states that are in a degenerate subspace of the energy, so you don't have to worry about the energy conservation, let's say. So
the definition isn't so general that you could talk about a constructor which is only obeying X, Y, Z physical principles and not W. It's, you know, so that it's
very general.
obeying...
It's completely agnostic about which principles you have.
Oh, right. Okay, sorry. You could be talking about systems where you increase the energy.
Yeah, you could.
But just for the thing that you're, you know, changing.
Well, I'd like to. So this is a definition of possible, and it could go both with false laws of physics or with true laws of physics, and it all depends on which principles you want to stick with. Now, because we know something about the laws of physics, we know that, say, energy conservation is a good approximation, is true in certain domains, but then if we want to actually make it, in fact, energy conservation is not a true principle because we have to upgrade it to incorporate relativity and all of that. But so that's a separate question. This is to do with which principles you think are right and which are not. And then that's a question for, you know, it's a separate issue. Here I'm just defining what possible and impossible means with some examples. And now your example was, in a way, assuming, I suppose, that energy conservation is true, in which case I was trying to answer to you that the oven by itself wouldn't be a constructor, even though it looks like it's working a cycle. And then I was giving you a different example now in quantum computing, where you're assuming that degrees of freedom that you're considering as a computational basis are you know, they're not eigenstates of energy and so on.
Yeah,
but it's very general.
I would still be arguing in the case of actually doing this quantum computing task of rotating in the degenerate eigenspace, and actually, you know, that the process of you doing that physically in a lab would.
Perhaps we should leave her get a small bit further into the seminar, because we're
sorry. Yeah.
Before we even she even gets to the definitions of what she wants to talk about.
There'll be more questions coming along with the first example.
Sorry, yeah.
No, but I think it should be clear enough now that you know, with the example of copying orthogonal states, at least you probably or the energy conservation, you should understand what is the difference between possible and impossible. It's just impossible means there is a finite accuracy beyond which you can't go in terms of implementing the task with the constructor. And possible is if you don't have that limitation. Okay, so now question is, can you find some consequences of the principles that you formulate in this way? And you know, can we have tests to check these consequences and so on? And so the first application that I wanted to talk about is this idea of using these principles of constructor theory to perform predictions when a given, you know, when you can't assume a specific dynamics in a context where either the dynamics is intractable or you don't know which dynamics you want to use. And so to zoom in a problem, we can look into this problem of hybrid systems, which I kind of find very interesting. So the problem is this: you have like a quantum system, so you know that it somehow obeys all the laws of quantum theory. And then you have another system, S, which is somewhat deemed to be classical, so it doesn't have the quantum features that Q has. And then kind of old question that's been around for a long time now is it possible that, you know, a system of this kind exists? Is it consistent? Does it make sense? Could it be a way to describe reality where you have a sector that's quantum and another one that's classical? And obviously the motivation behind this is that we think that gravity is best described by general relativity, which is classical theory. And then the rest of the world is described by quantum theory. And because objects have a mass and energy, they can gravitate. And so this type of hybrid seems to be perhaps a candidate to describe what's going on when a quantum object interacts with gravity. Now, this is a system, this is a kind of problem that goes beyond dynamics, because there are proposals to you know, describe quantum gravity. But we have a number of them, and you may not want to commit to any of them to approach this problem. And I think this was the reasoning that de Wit kind of followed back in the days when he was kind of investigating this problem. so his view was that quantum theory has like a totalitarian property. So he was trying to answer that question in the negative, saying that that system is not possible. So he said in his own words that the quantization of a given system implies also the quantization of any other system to which it can be coupled. And this means that quantum theory must immediately be extended to all physical systems, including gravity. And this is a theorem that he proved. So he proved the theorem under some assumptions that were still very dynamic specific to the effect of proving this statement. And then you can try to criticize this theorem. So you can say, well, this theorem assumes many dynamic specific features. So it assumes things like proper of the Lagrangian dynamics. And so it could be questioned whether it's general enough, because, you know, some skeptic could say, well, you know, maybe we have a classical theory of gravity that doesn't follow that paradigm, and we could still describe gravity classically. So could we make this more general as an argument? So could we have an argument that's kind of based on more general assumptions that hold for quantum theory, but also for other classical theories, maybe also for quantum theory's successor? And so my work has been to apply some principles of constructor theory, specifically from the constructor theory of information, to tackle this problem and make the argument more general. And that led to some nice development also in terms of ways of testing the non-classicality of gravity. So that's what I want to tell you about in the next part of the seminar.
So if I may ask, so do we agree that the Witt's argument is incorrect, or that it is limited?
It's not incorrect, it's very correct, and I kind of buy it completely, and I'm actually in his camp, so I would apply quantum theory without a doubt to most things, including gravity, and I don't have a problem with that somehow. But I think because I'm worried that there could be skeptics who might say, well, you know, the assumptions are very restrictive, I want to make it more general. And that's interesting, because it kind of leads us to this domain where you can't assume a specific dynamics, and you can still want to make statements, you know, that are valid and you know, they have a general applicability. So that's the argument is correct.
Yeah, because it sounds really weird. I mean, because the discussions we've been having so far are just so universal that it does. I mean, when you're talking about a constructor, it could basically, the anthropic principle doesn't even apply to it, because, you know, in another universe, I don't know, energy might not be conserved. But then his argument is very, very restrictive.
Right. So that's the point. So the point is that that's not constructor theory. That's something that we want to generalize. So it's an example, it's a starting point of a generalization. And I think what I want to do is to use constructor theory's principles that are much more general to make the same statement, but make it stronger. That's the kind of aim. I think you're completely correct. Yeah, I agree with that.
Yeah, so that sounds like a very difficult task that you're going to do. So that I'm very keen to see how the story ends.
Okay, cool. Yeah. I think it's not that complicated in a way that once you have these general principles, I mean, it's somewhat direct to find this result. But I guess maybe, as you say, we are so accustomed to think in terms of dynamical constraints that you know, this might be looking unfamiliar. So that's why now I'm going to take a few minutes to introduce this constructor theory of information. And again, there'll be some definitions, and I hope they are clear enough. Okay, so what we need is to have a framework that can treat both quantum and classical information on the same in the same kind of way, so that we can define a acceptable generalization of this condition of being quantum without using quantum theory. I think that's kind of the goal of this constructor theory of information. So, okay, to do this, David and I thought, okay, let's define a class of systems which we want to think of a generalization of a bit, so of a classical information medium. So an information medium is a physical system, a substrate that has certain tasks that are possible on it. So it's a kind of condition for the system to be an information medium. And these tasks are all permutation tasks on a given set, and the copy task, which is defined in this way. So an example is of an information medium is a system with a set X of attributes or states, which we can call 0 and 1, for example, on which these permutation tasks, 0 goes to 1, 1 goes to 0, and the identity are possible. And the copy task is also possible. So the task where you're sending 0, 0 to itself and 1, 0 to itself, to 1, 1. You see, this is a copy task because it's copying the value of the first slot onto the second. And not all systems have these properties, and not all sets of states have these property, but those that have, we label the information media, and the set of states with these properties we call information variables. So an information variable is a variable that can be permuted in all possible ways and copied. So this kind of defines a class of media. And then you can state some principles, that some constraints that this information media must obey. And the main principle is this principle about interoperability of information, which says that if you have two information media, so two substrates that satisfy that condition that I said, you put them together, they are still an information medium with an information variable that's a Cartesian product of the two information variables of each of the two information media. And if you work out what this means just in terms of permutation, you see that this is a kind of way of imposing that the distinguishable states of one information medium can be copied onto any other information medium. So information media are interoperable no matter what's their physical implementation. And this is a property that we all assume of information, but if you want to state it in terms of constraints on the, let's say, the possible dynamics of your systems, this is one nice algebraic way of stating it. And again, it's scale independent because this holds for systems that have any scale. You don't need to be in a macroscopic domain. So this is interesting for this reason too.
And so,
yes.
How do you come up with these principles? These are things that you logically expect of media?
Yes, I guess we all, I mean, this is with principles, it's a bit like, how do you come up with energy conservation? I think you observe some regularities in nature and then you say, well, this is one mathematical way of phrasing that. And in the specific case, I think it's because when we take two, this is a property of bits and qubits alike in the same way. I think they both have this property that it doesn't matter what substrate they are realizing. You can just consider the possibility of copying information from one to the other, no matter what's their physical substrate. Like, for example, you can have an electron that's a qubit, electron spin, and then you can copy the information into a photon polarization and then so on. And I think this is the same with bits. You can have transistors or other things. And somehow this refers to the possibility of, setting up some appropriate transformations, interactions that are available in nature so that this copy is possible. And this is making it formal in a way. So it's like defining a thing that is in common to all of these media with the same properties. And that becomes like in a way, it's an abstract property of all of these systems, irrespective of their physical details.
I mean, this it's very much like group theory and the definition of what is a group, and
Yes, I think it's nicely one aspect of this definition. There could be other definitions, by the way, they imply the same property. But what we liked about this was that it has some nice algebraic structure to it. Yeah. So I think that's why we went for this form specifically. Okay, and then you can prove an interesting theorem that there is a, so first you can define a new class of media and then prove an interesting theorem. So the new class of media is a subset of information media, if you like. So they are information media with at least two information variables, X and Y, whose union is not an information variable. So again, an example of this, just to explain where I'm going with this. If you take a qubit, you can consider two non-commuting observables of the qubit. And of course, you can think of their eigenstates. Now, each of these two sets of the eigenstates is a information variable because it's permutable and copyable by itself. But once you consider the set-wise union of x and y, so the set 0, 1, plus and minus, that set is not copyable specifically. And that means that the qubit is a super information medium because it has this weird property that it's the union of its information variables is not always an information variable. And so then you can show that there is this interesting hierarchy where, so you got information media, this class of systems here. Then you have super information media, which is like a subclass because they're more restricted. And then quantum systems are a subset of these super information media in the sense that super information media have all the qualitative properties of quantum systems. And this is interesting because somehow we've done this without using the formalism of quantum theory, but we have captured the, if you like, the information theoretic structure of quantum systems in this concept of super information medium. And this was going to be useful to go back to the Witt's problem to deliver that the generalized theorem that I mentioned earlier. So to do that, we need to, one extra thing. So we need to define a thing that's called non-classicality, which is not quite quantumness. So when we think of what it means to be quantum, that's a very interesting question. There are different degrees to which a system could be considered non-classical. And here I want to focus on a specific property. So the system is non-classical if it has at least two variables x and z, one of which is an information variable, and these two variables are incompatible. And incompatible means that a certain task is impossible on them. So it's impossible that x and z are copied simultaneously to perfect accuracy. And this generalizes the idea of non-commutativity to this super information framework. Note that it doesn't necessarily mean that both of these two variables are information variables. And that's a kind of subtle thing that you know, we can discuss maybe after the talk. So it's a slightly weaker condition than being a super information medium. A medium with non-classicality is not necessarily a super information medium, but it has some features that are not purely classical. Okay, now that we've got this definition, we can go back to the task that I set at the start and try to prove this theorem that I mentioned, or kind of state it and then discuss it.
So can you remind me what classical means here?
This is just a terminology. I define non-classical in this way. If you like classical, you can think of something that has just one information variable. So all of its attributes can be cast into an information variable, one that can be copied and permuted in all possible ways. Typically, a discretized version of a classical system that obeys Newtonian mechanics or Hamiltonian mechanics is an example of a system that is classical, because you can set up a big information variable that contains all of its dynamical degrees of freedom, and that's permutable and copyable in all possible ways according to the dynamical laws. Okay, so then we can now state the kind of go on to generalize the Witt's theorem. And to do that, we need three axioms.
Sorry, just before you go on there, I expected you to define information and the information content, something like Shannon information, but you didn't. You don't need that concept?
This is not about defining information. I think it's about defining the physical properties that systems must have in order to contain what we informally call information. I think Shannon simply assumed that different states are distinguishable, and he never thought of, it wasn't interested in fact, but his interest was more linked into a different problem, but he wasn't questioning, you know, what is it that makes a system able to contain what he called information, right? So he just assumed different states are distinguishable. We don't want to even think of what distinguishable means physically. So here we are defining, if you like, if you are defining information implicitly, it's the thing that can be carried by systems on which these tasks are possible. And these systems are called information media.
But you are not going to quantify it like Shannon information is essentially an entropy.
You can quantify it if you like. You can just take the cardinality of an information variable is the information capacity of an information medium. So in a way, you can just count the attributes within the information variable, and that will be a way of imagining, of defining quantifying the capacity of the medium.
Okay.
But in this case, we don't need necessarily to be quantitative to prove this result, because it's in fact a qualitative result. It just says so long as you have a certain degree of the width result that we were talking about earlier.
Okay.
So long as you have some sector of the universe which is non-classical, then all of the universe must be non-classical under the axioms that I'm going to state. And it doesn't matter to what degree it's non-classical. If you were interested in quantitative stuff, then yes, you can quantify it. It's a nice question, I think, because it comes out somehow this provides, this work is designed to somehow provide the foundations for Shannon's theory and make it rooted into physics, rather than assuming simply that these different states are distinguishable, which is what I think Shannon did, because clearly he was trying to solve a very different problem. And so somehow now you can integrate these two views and maybe kind of complement his work with this. Yeah, so
a naive question. What you're telling me here is just it's basically group theory. Is this accidental that these kind of properties are very similar to the properties of a set that then you define as a group if it has these particular properties, or is there a reason?
No. I mean, it's other than besides then it's just on the one hand it's convenient for proofs, but it's not, if you like, it's not an accident. Is a conjectured law of, it's a conjectural principle about information, then it has some mathematical form, and this mathematical form seems to have this structure. If you want to read more into it, I wouldn't know, because in a way it's a bit like maybe some properties of, say, the principle of locality, for example. You can think of it being manifested formally in some properties of, say, commutativity between different space, like the observers of space, like systems and so on. But I think that's, I see that more like as an accident in a way. It just so happens that it's nice to, it turns out to be expressible in this way. If you have ideas to see the other way, to think of it the other way around, I'd be interested to discuss that.
Yeah, I mean, what you say makes perfect sense to me, because you're just basically reviewing group theory for me. And it's like, yeah, of course. That's not surprising. Yeah.
Yes, well, here I mean, in a way, the whole of physics is group theory, kind of. You could say that, like we're using Hamiltonian mechanics. Yeah, it's but in a way, it's always the context in which the context in which you're using it and what you're saying about reality that's interesting. At least that's, as a physicist, I'm interested in that.
Yeah.
Yes. So, okay. So just to go back to this theorem, so the axioms I'm going to assume are locality, which you can think of it as a generalization of no-action at a distance, and you can formulate it in this framework. But if you want to think of what it means physically, it just means no action at a distance. Then the interoperability of information, and then you want some assumption about the fact that the dynamics that obeys these principles could be anything, but it has to obey this one-to-one feature. And
what do you mean by a one-to-one feature?
Just the dynamical law is logically reversible, if you like. So it's one-to-one. So it maps, if you think all the physical states of a system, the set of it is like the dynamics is mapping it onto itself, and you want it to be a one-to-one mapping. So you don't allow for merging, for example.
Yeah, so automorphism in group theory.
Yes, you can say that, yeah.
Perfect.
If you want to say it like that, but you can define it more generally. As I said, you can have a dynamical transformation that doesn't necessarily use group theory.
Absolutely, yeah.
right? So you could have, yeah, so as I said, this can be defined on a set of states, and then you have a mapping between these, so on the set. And then you can specify more properties of the mapping, but we don't need to do that for the purpose of this theorem. Okay, so we have these three things, and then so these are the axioms that are generalizing the axioms that we had, which were basically assuming Lagrangian mechanics. And then we can prove this interesting theorem that says that if you can copy, so if you can couple a super information medium Q with an information medium S through a copy-like interaction, so one that performs the copy task that I mentioned earlier, then the system S must be non-classical. So if you had a theorem where, if you had a kind of theory where you have somehow a super information medium Q, which could be a quantum system, coupled with a purely classical system, that would mean that that theory should have to violate one of these three axioms that we stated earlier. And this is a nice generalization that Vlatko Vedra and I came up with a few years ago. And it got us very interested in this stuff. And so then we tried to generalize this even more. So in a way, this was an abstract theoretical theorem. Then we thought, is there a way of making this more interesting so that it can suggest a way of even probing whether a system is non-classical by making it interact with some quantum system. So again, going back to this problem of understanding whether gravity has some non-classical features or not. And so that's the second thing that I'm going to tell you. So this is a kind of extra step where you're thinking, I can now devise a sort of witness of non-classicality for a mystery system S. Again, you can think of S as being gravity, but you can think of S as being whatever you like, so long as it satisfies some axioms. And this is the scheme. So the idea is that you can use two, not one, but two super information media to interact with S and extract, check whether S is non-classical. So this is an idea to devise a sort of test of non-classicality. And the idea goes like this. You can assume, again, two things: locality, again, and the interoperability of information. And then you can imagine of having to have two super information media Q and Q primed, and this system S. And the theorem says
sorry,
yes.
Could I just quickly ask, how is the locality part coming in here? How do you use it?
Oh, locality just means that when a task is performed on a given system, the observables of the other systems shouldn't be, the variables of the other systems shouldn't change. So it's a very simple form of locality. There's no action at a distance, if you like. And
okay, so it's not a relativistic.
No, not at all. It's a non-relativistic notion. I mean, it's a precursor, if you like, of the relativistic version. But it's just like what you have in non-relativistic quantum mechanics. The fact that because, I mean, in quantum mechanics, different, observables of different systems commute. And as a result of that, when you have, say, a unitary or a CP map that acts on one of them, you can't change the observables of the other systems. Mm-hmm. That's what it means. It's just, I mean, it's just formalizing it in a more general way with tasks, but the meaning of it is like this. Locality is needed, by the way, to also define information. So there's no sense in which you can talk about even measuring or testing something if you don't have this very basic notion of locality that somehow underlies the theory that you're using to describe your experiment. Does it make sense?
Yeah, I was just.
It's not Bell non-locality, so this is a different.
No, yeah, I was puzzled. Like, you are saying that this theorem that you're talking about is showing that gravity must be quantized or something, going along with what DeWitt.
Yes, let's say yes.
But it's not needed any input about the speed of light or any notions of causality.
That's very interesting. Yeah, I find it interesting myself. It doesn't say it's not applicable to gravity only, but it's you can apply it to a number of other systems if you like. So it could be any system that satisfies these features. They're very loose assumptions. I mean, we know GR satisfies this locality, just that it has a much more sophisticated version of it, but in particular,
I mean, if I was talking about the system S, which is meant to be my a priori classical system, you said it can be gravity, for example. What if I'm talking about, the metrics in space-time? It's not the statement about locality and being able to change the system in some way really depends on the metric in a more global way. It's
well, if you go local enough, then that doesn't matter. And if the theory has the property locally, then that's all this requires. And then if you have a theory that has a stronger property of locality, that's even better in a way.
But I mean, a problem with gravity is that there are no local degrees of freedom, really. No local diffeomorphism invariant degrees of freedom that you can.
Right, but these are like vector potential things. So they are not. I mean, if in the analogy, in the let's say, if you consider the the electromagnetic analogy, you can define observables in the sense that I say, which are not diffeomorphism invariant, but they're still copyable. Just like, say, the vector potential in electrodynamics is an observable in the sense that it can be represented by some Hermitian operator and it can be copied. But then it's not invariant under gauge transformations.
It's not clear that it's an information, that you can store information in it, or that it satisfies your first rule that it was.
Yes, it's copyable. I think that is true. Well, okay, in the case of gravity, I think it depends what scheme you're thinking how to quantize it. So I'm not sure. So talking about electrodynamics, that's somehow easier to talk about because we somehow agree on the way to quantize that. The vector potential is is a Hermitian operator, and it has a bunch of eigenstates, and those are copyable features of your system or your physical system. The only thing is that when you change gauge, then it will be represented by a different thing, but it's still copyable within that particular gauge you're using to perform your computations. So in that sense, it satisfies the property of being copyable. It's a looser sense of observable than, say, the one that you were using, which is the fact that they have to be invariant under certain transformations.
So are you then just showing that vector fields are quantum then, if they're coupled to some quantum system? You're not showing that gravity is.
No, I'm not showing. Well, you can treat gravity as a vector field if you like in certain approximations, but you don't have to use. I'm not talking about fields here. This is just now an example because you asked a question about that. But I'm not assuming. I'm just assuming a partition to subsystems and the fact that you can define these copyable degrees of freedom. I think it could be interesting to look into seeing what happens when you consider these copyable degrees of freedom. What happens to them when you perform certain transformations and see what occurs in different coordinate systems and so on. But I think the copyability is in a way invariant. It's just that different things are copyable in different maybe coordinate systems. So that's how I think about it.
Sorry, I have a question. Hi, sorry.
Hi.
So I had in mind a vector potential that is really classical. I mean, for instance, in cold atoms, in quantum gases, you can take a quantum gas and you can shake, you can rotate. Mm-hmm. And so this is a way to simulate, so to create an effective magnetic field. But we know that that is really is a gauge potential in principle, but it's poorly classical. So I was wondering how this can match with the Witt theorem and what you're saying about the quantization of external gauge fields.
Well, so the fact that you have an approximated description of something as classical doesn't mean that the thing is classical. It just means that in certain domains you can model it as classical. But here we are talking about a specific experiment in a way where you have two. Okay, now forget about the general theorem and let's just focus on an example. You have two charges. We can even talk about the electromagnetic field. Maybe that's helpful.
Yeah.
And these two charges are initially non-entangled, and then they interact through some electromagnetic interaction in a way that they don't interact directly, so they have a kind of mediating interaction through this field, if you like, and at some point they become entangled. And now the theorem tells you that if you took care of the fact that the radiation that caused this interaction had, some features so that the wavelength wasn't larger than the distance between the two charges, so the interaction was really pointwise and local, then whatever mediated this interaction has got to have these non-classical features. But the experiment is very specific. It has to be done in a certain way where, there is a pointwise interaction between Q and S and Q prime, but not directly.
But I guess you're assuming inertial frame, because I guess in non-inertial frame.
I'm thinking now it's a very local, yes.
Okay, it's
definitely.
It's related to the idea that you have a very local constructor, right?
Yes.
So,
yes.
More relativistic, and okay, these are indicated for the assumption in all the situation. Okay.
Yes, you should think of it, but I think in most laboratory scale experiments that we can do right now, these assumptions make sense.
Yeah.
If you wanted to generalize it, I think you could, but it doesn't, you can somehow always bring yourself to that situation, do the experiment, and then, so if you prove quantumness at that level, then there should be some quantumness also.
No, yeah.
In more general theorem.
It was again back to the gravity is not an inertial force. So again, there are intrinsically non-inertial. Is what we know gravity, right?
Yes, but you can always consider an experiment with such terms are not relevant.
Yeah.
In that regime, let's say in a, if you like, a quasi-Newtonian regime, you can apply this kind of argument.
But you're not really accessing gravity in that sense, then. So
you're accessing something that is a limit of, so gravity is always there in a sense. So you can think of it as space-time geometry, maybe. Maybe that's more appropriate.
But it can be just an acceleration. In principle, I can simulate that physics with an acceleration.
You can, but then that acceleration would have to have, if it's local, if you look out. So this just tells you that if you want to treat that thing that mediates entanglement as a third system, as a mediator, as a dynamical mediator, then whatever you're using, acceleration field or non-field or whatever, it has to be non-classical. It's got to have these non-classical degrees of freedom. If it doesn't, then you can still do it, but then you have to violate some of these properties. So it's either non-local or you have some other problems with the interoperability of information, or the interaction is direct between Q and Q prime and so on.
I think it's the locality that's gone for gravity. I mean, people that push entropic gravity, I think would not agree with.
I don't think so. I mean, even just gravitational waves are a proof that actually there is a local property. So this no action at a distance is a pillar of, in fact, that's why Einstein introduced the whole idea of, right, of generalizing Newtonian gravity, right? So you wanted to avoid. So if you take locality as no action at a distance, I think theories of gravity that we're using now satisfy that.
But that doesn't mean that there is a quantum degree of freedom behind that.
No, that doesn't mean that. But let's say if you assume that, plus you do this experiment and you witness this entanglement, then you can use the argument to conclude that that's the claim that I'm trying to explain, that you can use the argument to conclude that whatever mediated this entanglement, if you want it to be to satisfy this property of locality and the other axiom, then you have to include non-classical.
My problem is that I don't see the locality there. In the gravitational wave case, the waves are coming in from some you have to include your
yeah, but the
black
locality,
hole, distant black hole in the problem.
right? But okay, then so locality is a very simple property. It just says that if you have a subsystem and you do something only on that subsystem that involves only its degrees of freedom, then no other degrees of freedom should change unless there is also an interaction with them and so on. But if this system is isolated and you're only acting on it, this shouldn't propagate elsewhere.
So maybe if you say it like as causality, that would make a lot more sense.
I'd rather not talk about causality because that's somewhat, I think in physics that has a bad reputation in the sense that some people say that doesn't make sense to talk about causality because of the time reversal symmetry and so on. So I prefer to stick with locality.
But I mean, yeah,
you call it no action at a distance. Maybe that's better.
Yeah, that's a lot better. Yeah.
Just call it like that if you like. I mean, this is Einstein's locality.
Yeah, you're not here to prove to us that gravity is quantized. You're basically, yeah. I mean,
no. I mean, okay, but the validity of the theorem is about that. So in a sense,
yeah.
And the theorem does apply to gravity.
Absolutely. No, I agree with you. I'm just saying, yeah, us kind of trying to force you to prove to us that that gravity is quantized maybe it's not fair because,
no, I mean, this doesn't alone by itself doesn't prove that gravity is quantum at all. It just says that if you were to do an experiment of this kind and convincingly argue that, say, your experiment satisfies these conditions, then you would be able to conclude that whatever caused the gravitational entanglement is quantum. So I mean, it's non-classical in this sense. But again, gravity is just an example. You can think of other things. And I think in a way, DeWitt was interested in gravity, but you could think of equally of S as being like a different system or a kind of macroscopic system, a biological system, and so on.
Could I just ask again a little bit more about the locality thing in gravity? Because if I feel like to have a notion of locality like you described, where if I do something here to this system, it doesn't affect other systems in some way that they could have interacted with. The thing that you would be thinking about there is the the speed limit, the speed of light, that things that are space-like can't interact. But even to talk about that, you've had to put down a metric. You've had to talk about classical general relativity.
Yes, but I'm not talking about. So if you want, you can model that with the velocity of propagation of some.
But so just to talk about it, you have to put your experiment somewhere in a space-time-like picture, or at least it seems that way. I don't know how I would talk about things not being able to interact. You can have a very
local
with gravity as well. If I
of a point in space-time, and then you have two distinct systems there, and then if you do something to one, the other one doesn't change. That's what we do in quantum computing, by the way. It's not we never actually think that we are in. So
right. You can for all intents and purposes isolate your system. But if you're talking about gravity and doing something here, how do you stop the propagation of whatever you've done out in the form of, say,
you don't stop it, but the propagation has certain features, and they satisfy this definition, because if you were to stop it, then it wouldn't propagate.
But we know from general relativity that whatever you're doing there, it will propagate out in gravitational waves, and it will only affect things that are not space-like to the region of space.
Right, but there is something propagating. There is something propagating. So the two charges, if you think of the masses as charges, in this case, you can think of QQ prime as being two charges, generically speaking. And then if they're sitting alone by themselves and they're not doing anything, there's no way, so they don't interact at a distance. There is a medium in between, which we usually model as a field. And that is the system S that mediates the interaction. It doesn't mean that you have to model locality in this way, but that's the best way we've come up so far with fields. So any theory that has that representation in some regime satisfies this principle.
But are you not then just assuming a classical background space-time of some sort to have that?
It does, but you won't entangle the two systems. That's the point. You can do, say, quantum field theory in curved space-time, for example. That's one way of, say, treating gravity classically.
Yeah.
But I won't generate entanglement between Q and Q primed in this way. That's the statement. If you could generate entanglement, then you would be able to rule out semi-classical models of gravity because they don't work to model that. Or you would have semi-classical models that are non-local. That's also possible.
So, sorry, are you saying that you can induce or mediate entanglement between Q and Q prime if they are space-like in semi-classical quantum field theory? Or sorry.
No, you can. So you can think of a very contrived theory that is non-local and can mediate entanglement, which is not the kind of theory that we expect gravity obeys, but it could be that there is such a theory that's non-local and has this, there are some of these absorber theories. So there are some of these attempts by Feynman and people like that who try to kind of look into ways of, I think Wheeler and others, everyone tried to look into ways of avoiding fields and still being local and so on. And then these attempts exist and they may still generate entanglement, but they wouldn't comply to this locality that I'm talking about. So in that sense, there are still, you can think of classical models that could entangle, but they violate locality or the interoperability of information. But if you don't, gravity as we know it satisfies both. So in that sense, if we want to stick with the theories that we think are plausible for gravity, then if we were to observe entanglement in this context, we would have to conclude that gravity is non-classical, fundamentally speaking. In
the context, if you have two time-like regions where you've done something, Q is down here and Q prime is up here, and they're time-like related.
Right, but they're not.
Mediated entanglement in that way. You use that to show that gravity must be non-classical. Is that what you were saying? Yeah.
Yeah, but here we are thinking Q and Q prime are space-like separated, and they in a way they start in a way that they are unentangled, and then they evolve towards a state where they are entangled. So that's what we are thinking in a given coordinate system.
Sorry, but isn't that what you said is impossible in curved space-time quantum field theory? You can't entangle.
No, you can't.
So then you have not shown that gravity is non-classical? I'm just trying to pick out.
Sorry, I didn't understand your question. You're asking me whether.
So from what I can see on the screen, it's if S can locally mediate entanglement between two super information media, then S is non-classical.
Yes, that's right.
And I thought what you just said was that gravity in the framework of curved spacetime QFT could not mediate entanglement between two space-like quantum systems.
Correct.
And so therefore...
Indeed, it's not. So, okay.
So then I thought, okay, that's the space-like part is why it's not locally mediate entanglement. That's a non-local thing. So I've not.
No. Locally just means that Q and Q prime shouldn't interact with each other directly, and so there should be a mediator. And also, this should comply with this locality principle that I said, that when if you have Q in isolation and you do something to it, S and Q prime shouldn't change as a result, unless they are interacting with it, of course.
Right. So in order, so we want them to be able to, we want to locally mediate between Q and Q prime to show that gravity is not classical.
Yes.
From this theorem, right? So then that's why I was thinking, put Q and Q prime time-like related. Q prime is to the future of Q, or the quantum system is to the future of the quantum system Q. And then you would get your locally mediated entanglement.
Okay, this is a variant of the experiment, and I think it has some, well, this is so it's an interesting question what you're asking. It has some problems because it doesn't quite, the argument doesn't go through in the same way. So the fact that you're considering a time evolution of Q into Q primed, it's mediated by another system. is not the same as what we are discussing here. So in fact, there is a general, so I'm kind of working with some students on a generalization of this theorem right now, which goes along the lines of what you said, but it's not, it doesn't transfer automatically in this other scenario, but it's an interesting question.
Okay.
I'm not sure though how this connects to the quantum Euclidean curve spacetime aspect that you mentioned.
Just because I was trying to actually imagine an explicit setup where you could say, because in this explicit setup, gravity mediates entanglement, then gravity is quantum or non-classical. Sorry.
Right.
I wanted to say that, you know, and
okay. That's exactly the way to think about it. And somehow this experiment, if you were to perform it, would would refute, if you observed entanglement and you assumed all of these things, then you'd be somehow saying that quantum Euclidean curve spacetime can't model this. So it's refuted somehow by that observation. I mean,
but does curved spacetime quantum field theory not, to, you know, really good approximation, give us what we observe?
Mm-hmm.
You know, so by that logic, wouldn't you be saying then that gravity is classical? For, you know, it's not satisfying the start of that theorem there, right?
Well,
if it's not actually locally mediating entanglement between two quantum systems, maybe I should, you know, wait again to
No, I mean, this is the end of the, I think we can stop, right? In a way, I only have a few more slides, and I'm happy to actually continue the discussion, because we also
but by all means finish your slides. It's a couple of slides.
Okay, well,
we can postpone the discussion until then.
Okay, that's fine.
May I suggest a quick break, because I noticed Kara's water was finished. So I just wanted to give you a chance to go fill up your glass of water.
Oh, that's very nice of you. Yeah, I think it's a good idea, actually.
Yeah, I mean,
just fill it here, okay?
Yeah,
I'm coming back in a sec. Yeah.
Yeah, I come with a big jug.
Oh, this is an impressive amount of water.
Yeah, well, I mean, it's a beer glass, but I fill it up with water, and yeah.
So I think the theorem is this, and so this is like the second version of the generalization of the Witt's theorem, and I guess, you know, if you want, you can think then of applying this to gravity, which we already discussed, and this is how we started discussing a number of possible ways of implementing this as an experiment. And this is some kind of application, but we already discussed it. And currently there's somewhat a kind of discussion about how to do it, whether it's feasible, you know, what kind of masses you need and so on. But I didn't want to enter this because this was more about constructor theory rather than about this experiment. But if you're interested in this specific line of inquiry, there are also works by other groups that have been looking into these things. Sugato Bose in London and his group, and then other people in Vienna, etc. I'm happy to also give you the references if you're interested. Okay, so then, like, the summary of this is to say that so these principles that underlie the theorems are, again, independent of the dynamics and the scale, so that's nice. And then again, the second theorem suggests a class of experiments which somehow can rule out classical models for any mediator S that satisfies these principles. You can apply this to other systems, and that's very interesting because it's all in the domain of, you know, there is this debate about whether quantum theory is really universal or not, and this could provide some ways of actually, you know, devising some tests to check that for specific systems that we are doubting could be quantum or could obey quantum mechanics in the way that we think it leads to quantum coherence, at least. And this is a bit like, so the way I think about the theorem is a bit like the generality that, say, Bell's theorem has, because Bell's theorem also has this feature that it doesn't really care about which specific dynamics you're using to describe your experiment, but if you can measure some correlations that exceed a certain value in a given setting that satisfies various axioms, then you can exclude a whole bunch of dynamical models that use locally invariable models to describe that experiment. And that's very powerful because you can apply it to a number of things without worrying about specifically what dynamical law you're using to describe your systems. And this theorem has the same kind of spirit. Yeah, and I guess this was in a way, the summary of this section. And I'm happy actually to break here and to have more discussion because, there was a part about thermodynamics, but I guess it's because we focused so much on this one. I'm very happy to continue the discussion along these lines. And it seems to me it's a natural breaking point. So I would stop here with the seminar, and I'm very happy to continue discussing, and kind of thanks for listening, for the questions.
Okay, thank you very much, Kira. That's obviously generated a lot of discussion. And your experiment with the two masses has yet to be performed, of course. So the question is out with regard to quantum gravity, or whether gravity is quantum or not, experimentally so far.
Yeah, I guess that was the somehow the interest that so this caused some interest because both Sugauter's team in London and we converged on the same degrees of somehow the same orders of magnitude for these masses that should be superposed, and this was around it's about 10 to minus 12 kilograms, roughly speaking, with the back of the envelope kind of calculation, which is massive, but not as massive as, say, Planck's mass. And so somehow this was surprising because it's going to probe a regime where, say, GR's effects are not really important, but the quantum effects are somewhat relevant. And I mean, if the experiment turns out to be showing some entanglement when it will be performed. So in that sense, I think that created a lot of interest, possibly because it's not, I would say it's somewhat more within reach of say, the experimental capabilities than perhaps other proposals that have been around for a bit.
10 to the minus 12 kilograms is much smaller than I would have expected.
It's it's not very small, but it's smaller than what it's somewhat encouraging.
It's on the line of the mass of relatively small molecules.
Yes, it's about the size of a human cell. Really, it's kind of it's a bit larger. So currently they are doing this macroscopic interference experiments with buckyballs and molecules that have structures that are a bit lighter than this, 10 to minus 17, so on, kilograms. And I think the thing is now to find a suitable system where you could actually somehow create a superposition that can allow disentanglement to be created. So I think various groups on the experimental side are kind of looking into this. Of course, it's a substantial endeavor, so it may take time.
An improvement of 10 to the minus 10 to the 4 is significant.
It's very significant, yeah, I think so.
But imaginable.
Yeah, it's not as far off as much larger masses, which is what one might expect. If this is something that is of interest, I can share. Wait a second, let me just share this thing that, hang on. Oh, sorry. Let me just kind of go ahead and find something that I wanted to show you. Wait. Right. So this is going to confuse probably the discussion even more, but this is something that is nothing to do with constructor theory right now. So this is a kind of model for what this experiment might look like. So here we're really dealing with quantum theory. In fact, we calculated these things with linearized quantum gravity, so it's a very simple calculation. But that's the idea that we are kind of thinking about. So you have two interferometers, which could be Mach-Zehnders, but they need not be. So they could be anything that can create a superposition of different locations for each mass. So the first mass is superposed across two different locations, and then the second mass is superposed across two different locations. And then you can consider some interaction with a gravitational field, and there is a coupling. And when you plug in the numbers, you get a phase for each of the branches of the wave function that has this form. And by plugging the various relevant numbers, there is this mass that is about a 10 to minus 12 kilograms, and then delta t is something like a microsecond. For the entanglement to be maximum, so that would be a detectable phase, if you like. And so that's how you get these numbers that I mentioned. And I think this is we converged with two different reasonings and coming from two different directions. I think both Vlatko and I and Sugato and his group, we kind of came up with the same numbers and more or less the same scheme. And there was somehow this nice check that there is something right in what we're doing.
How is gravity playing the role of the entangler in this?
So you can model. So one way we model it in a quantum mechanical way is to imagine a coherent state of gravitons, of many gravitons, and each of the masses has a coupling term with this field that is like a kind of interacting. It's the usual interaction term that comes from the linearized kind of quantum gravity model. And the gravity is entangling the two masses because the fact that the two things are in a superposition gets the field kicked in different ways in each of the branches, and that leads to a different phase in each of the branches. So it's a bit like I would say you can model it with this coherent state picture, which would work for photons just as well. So in the way, you can think of these two masses as two charges, and the same reasoning would apply. So in a way, you're not really exciting. There never is something like a graviton being emitted, or because we know that's not something that we can do. But what happens is that there is a field of superposition of many different numbers of graviton states, like a coherent states, which gets kicked by the mass distribution, and that's what entangles the two masses in this model, which is how we get the phase. And it's kind of counterintuitive because I guess the two non-commuting degrees of freedom of gravity are evident in the Hamiltonian, because you have a term which is proportional to A dagger A, if you think of the number operator, and then there's another term in the Hamiltonian which is proportional to A plus A dagger, right? So it's these 2 degrees of freedom that in the Hamiltonian that allow for the entanglement to be generated. And you can model it in this way because it's low energy, so these masses are very slow, and it's kind of an acceptable approximation at this scale.
So this means that the vacuum is filled with virtual gravitons, right? So this will be the assumption.
That's right. Yes.
Okay. So
to do the calculation, yes.
Okay. So
but it doesn't mean that if we observe entanglement, this corroborates this model of quantum gravity. It doesn't mean that this proves that there are gravitons or anything like that, because the assumptions are very general. So it could be a different model of quantum gravity that leads to this.
Right. But still, you need the virtual particles somehow.
Yeah, that's right. So somehow some quantum-like particles should be there.
Yeah.
And then one can discuss whether it should be gravitons. I think there are some interesting works by Dan Carney and collaborators where they try to say a bit more about what you can, by additional assumptions, what you can say about whether it should be a graviton or not, and what kind of spin it should have, all of these
exactly.
things.
Somehow one should be able to measure the spin virtually. I mean, in the experiment with protons, where they are able even to measure the spin of a virtual quarks. So in principle, the spin of the proton is just not the sum of the 3 quarks, but also we have to take into account all the virtual quarks that appear inside the proton.
Yes. Yes.
I mean, maybe there should be a way indeed to distinguish in terms of the spin. That will be very interesting. Indeed.
Yeah, I don't think this is possible yet. I mean, in this scheme, the spin is not relevant, but I think maybe there is a way of doing that, and that's very interesting to look into.
Okay.
Yeah.
Is there a? Sorry, I didn't.
No, please go ahead.
Is there like an experiment to do, or what am I trying to say? It seems like you could just calculate what you expect from that experiment with curved space-time QFT, and then if you just get something that's not that, then that gravity is not classical and particles are fields. That's not the right picture. So it's like a precursor to even imagining that linearized gravity is quantized. You just can show that it's not this picture or whatever.
Yeah, exactly. I think the point is to say that you can rule out, it's not confirming any specific model of quantum gravity, but it's somewhat saying that you can rule out a set of classical models that obey these assumptions.
Yeah.
And so, for example, quantum field theory in curved spacetime would be one such model.
Yeah.
Then other collapse models also can be ruled out at this scale.
Yeah. Okay. Yeah. Yeah, thanks for answering all my questions throughout the talk at such length as well. And on the last one, I didn't realize as well that, you are saying here's the experiment that we need to do to tell whether or not. I thought there was already some sort of proof based on evidence we already have.
Well, we don't have that evidence, unfortunately. Actually, I think I discovered by talking to various people that we don't even have an experiment of this kind for charges. Of course, we know that the light is quantum. We don't need an independent proof, but somehow it would be interesting experimentally to do an experiment of this kind where you have two maybe charges like electrons or something and you get them entangled like that. But I don't think we've done that. So yeah, it's interesting. I mean, with gravity, of course, it's much more challenging. I guess there are also all sorts of other forces in, you might have to make sure that there are no other interactions that somehow fake the entanglement or mask the gravitational entanglement. So these are very, very kind of difficult things to do.
I've seen sort of similar looking experimental setups in the context of the gravitational collapse of the wave function, like this idea that came from Penrose, I think.
Yes.
I don't know where that idea sits now, but is it very similar what you're describing, or is?
I think the gravitational collapse so I think you can test gravitational collapse models in some settings with a single mass, and that will tell you what it will tell you. Let's say if you refute some of those models, is that the models are not viable. Those models are not viable, and then you must stick with quantum theory, unitary quantum theory at that scale. But here we are trying, because we're using two masses, somehow you pay a price of complexity in the experiment, but then you can make it more general because it rules out a huge class of other models that are classical. So somehow it's not just a specific, you can always make a prediction with a model and then compare it with a quantum model and say, oh, in this experiment, I can see a difference in principle. But here we're trying to be a bit more general that it's really like ruling out classical models that seem plausible because these two principles that we're using are reasonable and somehow general enough. So that's the aim of this. That's maybe the additional feature of this experiment. And somehow the fact that it's model agnostic, so it's not. So to calculate that order of magnitude, you need a model, but somehow to think of the scheme and then to rule out classical models, you can think of a more general scenario where you're not committing yourself to a specific dynamics. So long as you measure some entanglement, you can conclude for whatever non-classicality being there.
I had another question, but if someone else wants to go first rather than me just rolling them on, then
I mean, we always learn from the questions as well. So I'm very happy.
I think Tony wants to ask a question, so we can.
Yeah. Go ahead. Yeah.
I wouldn't mind something a bit different. So it seems that, but you know, I don't understand much of this. I don't understand quantum gravity at all. But it seems to be somewhat independent of it. You seem to want to make some axiomatic system which is more general than quantum mechanics. Is that right?
Yes. Yeah.
So there are axiomatic approaches to quantum mechanics, and in what way, you know, what kind of axioms are you leaving out to make it more general?
Right. So these axiomatic approaches are trying to derive quantum mechanics fully. So they want to get things like continuity. So there are some, well, Hardy has some axioms, and then there are others. And I think they are more restrictive because they really want to single out quantum theory as somehow the theory.
Yes, so you want to generalize, so you want to leave out some of those axioms.
Yes, and I'm leaving out.
Make some conclusions.
Yes, that's exactly. I think I really like the way you are putting it, because it's a very nice summary of what I do, what I would like to do. And the reason why this is, I mean, my rationale at least to be interested in this is that in that way you will, so if you just get axioms that single out uniquely quantum theory, you don't leave in the flexibility for the theory to change, perhaps to incorporate gravity or whatever else we might want to do in the future. Whereas in this case, we're thinking of these principles being general enough to be robust against these changes of formalism. So that's what it's if you like, it's a conjecture about capturing some general features of quantum theory, which I'm expecting that next theory will still have. So things like the concept of a superposition or the concept of entanglement in an appropriate generalized way, by leaving out specific formal features such as, I don't know, Hilbert spaces or density operators and so on, which may not.
But are you keeping the probabilistic nature of the theory?
Yes, in the form of. So you can so in that diagram that I showed very quickly with superinformation media, you can add some further axioms that allow superinformation media to display a probabilistic structure, like exactly quantitatively like the one, like the structure of quantum theories. So there will be something that resembles what we usually call the Born rule in these generalized systems, but it may have a different, it may have a different aspect, a different formal expression to the current Born rule that we have. But there is unpredictable. So what I'm saying is that there is unpredictability in these generalized quantum systems. So there will be a quantitative version of it that includes probabilities, and therefore the answer to your question is yes.
Yes. So basically, what you want to not have is some correspondence with a Hilbert space.
Yes. Well, one thing that may not be there is that, but perhaps there are other things I can't think of right now. Hilbert spaces not representations in terms of Hilbert spaces may not be
appropriate.
Necessary. Yeah, it may not be appropriate, and other things could break as well. For example, the possibility of having a tensor product structure, perhaps subsystems should be represented in different ways, etc. So, and possibly, I think someone who is more into formal aspects or mathematics than I am, I think might have even wilder ideas for how to represent one of these superinformation theories. But yeah, so you're it's exactly right what you said, that we want to be not just to derive quantum theory from axioms, but derive a general set of constraints that quantum theory satisfies, but are general enough to also be satisfied by a bunch of different other theories.
Okay, thank you.
Yeah, thanks.
Ian, do you want to go first?
Yeah, I'll go again. Yeah, sort of related, but going back to when you were defining an information variable and you had the permutation and copying, and then you said that the two information variables, X and Y, one where it was 0 and 1 or up and down, and then the other one where it was plus and minus for a qubit, how when you combine them, they didn't form an information variable. And that was kind of a key feature of what sets, say, a qubit aside from a bit. And so that sounded like it was incorporating the notion of just superposition itself, because that's what's somehow going on there that's different.
Yes.
And then I didn't see something where you say incorporated entanglement at some point, and I was wondering,
so if I had gone more into this various things that we proved in those papers, I would have zoomed in closely on entanglement. And so entanglement is you can generalize it in this framework in terms of you can give an operational definition of it that doesn't require you to talk about the usual kind of separability criteria and various other things that we do in quantum theory. But the thing that is needed in order for entanglement to be allowed in superinformation media is the fact that, so it's an additional possibility of giving tasks, and these tasks are basically one-to-one logically reversible transformation that involve plus, minus, and 0 and 1. So you have to be able to perform certain logically reversible transformations on the joint set of plus, minus, 0 and 1. And this, in addition to the non-copiability axiom, allows you to recover this generalized notion of entanglement. And this is interesting because it somehow tells you that it's not just enough to, even in quantum theory, I think what you need for entanglement is not just superpositions, the fact that you have some superpositions around, but also the possibility of course, of interference, which means that you have to have some reversibility in the transformations that you're applying. I mean, an interference experiment, if you like, is a simple example of a reversible permutation that involves not just 0 and 1, but also plus and minus. And I think, so I think it's possible to talk about entanglement and to derive it in that context, but you need this additional assumption, which you don't need in this second, I think the assumptions are still needed for proving the theorem, but I think in regard to this system M, the non-classicality of M is a weaker property than superinformation, precisely because it may not allow you to have this full control on the non-classical states of M. So you can think of it as being something that is not a fully fledged quantum system. It's something in between. It's certainly not classical, but it's not necessarily fully quantum.
Yeah. There are those boundaries that come up with Bell's theorem and sort of everything that goes in between, how information can be conveyed classically or signaled classically to what's allowed in a quantum system. And then you can go beyond a quantum system in that things can be even more correlated and still not violate causality, right?
Yes.
Does that come up in? Is that part of what this? Your pictures of superinformation.
That's exactly correct. I think those theories will comply with locality, but they, in the way that I was kind of envisaging, they may be superinformation. They may support superinformation media, and in that sense, you can think of these theorems as applicable to those theories too.
Have you done explicit, mapping of? Oh, when people talk about so-and-so levels of correlations, that's this area in our diagram.
No, I think that's very much, it's something that would be nice to do. I think I've been, it's an interesting direction, and it's exactly the kind of thing that this this construction should be helpful for, because it could help you understand what are the physical operational properties of those theories, besides the fact that they say violate certain inequalities by a certain amount. And yeah, so I think that's one possible direction of research which is open. Yeah.
Cool. Thanks.
Yeah, thanks a lot for the questions. Yeah, very, very nice.
I have another question.
Yes.
So this is not a question. This is kind of like a comment or something that that was very interesting to me. So you mentioned that for this experiment, the mass of the particle they would need is around 10 to minus 12 kilogram, which is a mass of it. And you mentioned a buckyball. And as many of you might not know, my background is in nanotechnology. Back when I was stupid,
yes.
I didn't know that physics is the way to go. And I remember when we were looking at buckyballs, that was specifically kind of the region where we knew classical physics doesn't work, and quantum physics, you don't necessarily need it, and we called it mesoscopic physics. So yeah, it was kind of interesting that as we're discussing kind of the connections between the quantum and the classical, and the mass scale that you mentioned, and yeah, you pointed out the buckyball, which is what people study in nanotechnology. And I was just thinking, yeah, this is a very interesting connection. Yeah.
Yes, I think this area is somehow, I mean, somehow is the area where maybe the skeptics who think that quantum theory may at some point cease to apply at a certain scale. This is where they might expect perhaps at a certain scale in that region to see things like collapse of the wave function if they pertain to some dynamical collapse theory or Penrose collapse or whatever, or perhaps some different behavior from the one predicted by quantum theory, etc. I don't think that's the case, so I'm expecting that quantum theory will work.
Oh, absolutely.
But I think there is still, at least maybe, I don't know how widely spread is this attitude, but somehow, at least in my own field, there's always like an adversarial, so there's some sort of part of the community that's still doubting somehow the universality of unitary quantum theory. And so it's cool to maybe think of experiments in that area, as you said, where we haven't quite managed yet to conclusively show that there are obvious quantum effects or quantum coherent effects, such as interference experiments. But I'm hoping that technology will get us there soon. And it's nice to think of what this means for maybe other, our own general view about quantum theory and how general it is, etc. So yeah, I agree with you.
Yeah, what was really interesting is that whenever you wanted to give an example, you would say, well, let's think of an example of a simple quantum system. And it's only in and you said it would make more sense. Yes, it's only in a physicist group that you go, use an example of something that makes sense.
Yeah.
Because of course, quantum mechanics makes sense. It's very intuitive. Why would people call it non-intuitive?
Yes, it's a mystery to me. I think you're right that somehow because we're working with it so often, then it becomes almost natural to think of things in. And I think it's nice also in terms of information theory, I guess, because it has this, quantum systems have this discrete structure for the eigenvalues and so on. And so it's really natural to think of quantum theory first, I'd say. Yeah, it's a good point.
Yeah.
Yes.
And one last point was that when you were kind of mentioning the pioneers of the field, like David Deutsche, and then I saw a lot of your papers are with him. So you're one of the pioneers of the field as well.
Not really. I think I guess. Well, I guess what happened then, I think it was that initially, so David came up with this idea here, and then other people came up with it elsewhere. And then there was like a very nice, tightly knit community of people talking about these things. And then it slowly grew into different maybe research groups around the world, and some are here still in Oxford, others are elsewhere. But it's kind of nice to hear these stories at the beginning where there was this interesting, sociological aspect of a new idea maybe that's growing, and people are trying to try it out, and there are lots of skeptics to convince and so on.
So what is your background, and how did you end up with working on this stuff?
So I'm a physicist, and I kind of was interested in quantum. So I became interested in quantum information in Turin when I was doing my, my master's. And then I kind of looked around for PhD possibilities and for places where quantum information was somehow developed nicely. And then I applied to various places, and in the end I got some kind of place in Oxford and then so I came here. But then I wasn't interested in constructor theory yet. I mean, I wasn't thinking of, David wasn't my supervisor. I think my supervisor is Arthur Eckert. He was Arthur Eckert. And I think initially I thought I would work on some conventional quantum computing topics, but then I got interested in von Neumann's work because of quantum biology. And then I stumbled upon David's stuff because I was looking for constructor theories of the universal constructor, and then somehow, and then that's how the collaboration developed. It's interesting. I think in a way I'm interested in a bunch of fundamental problems. So happens that constructor theory was very interesting, and maybe some tools are more general than the ones that we have from, say, standard quantum theory, but I think I kind of like to integrate things. And maybe I wanted to see whether there was some application of these general ideas that David had, which sounded initially very philosophical. So I was hoping I would find some ways of applying it to real physics. So that's how I kind of came into.
Because I assumed your background must have been in, I don't know, formal aspects of quantum field theory or quantum gravity.
No, not at all. I think my knowledge of quantum gravity is very limited. In fact, is limited to the to the linear regime in a way. And the way I came across this problem was mostly because I was interested in this universality of quantum theory. And so gravity is where one of the reasons why this is challenged usually. And that's why I ended up kind of thinking of this application. But yeah, I would like to learn more in general about, quantum theories of gravity, non-perturbative approaches, and so on. It's something I don't know much about.
Yeah, fantastic. Yeah, I really enjoyed it. Thank you so much. Yeah.
No, thank you. Thanks a lot for the questions. They were great.
Thank you very much, Kira. Maybe I will stop the recording. Just at some point we should stop recording.
Yeah, sounds great.
Okay, thank you very much for the seminar. We don't have to leave. I will just stop the recording. Okay, thank you.
Yeah, no, it was great.
Very nice.
I enjoyed the questions, and it's, as I said, it's very nice when there is some reaction, because otherwise it's not very interesting for the person who's speaking. So you really made it very, very entertaining for me as well. So thanks.
Oh, and I'm new to DARIS, but I must say, Denjo, I love these seminars. They are absolutely fantastic. I mean,
before this praise continues, I'm just going to stop the recording.
Yeah, maybe better.
Yeah, I think you haven't stopped it yet. It tells me.
I think it still says.
Oh, sorry. No, I answered the wrong.